So, we were talking about slag cements yesterday, and we were trying to understand what concerns we may have with respect to durability. In most cases, as far as chloride attack is concerned or durability parameters that lead to chloride resistance are concerned, you always get a positive response when cement is replaced by slag. Okay. However, there is an obvious issue that can come about whenever cement is replaced by any mineral additive. We have discussed this briefly earlier, the fact that you have lesser lime in the system, lesser calcium hydroxide in the system may lead to conditions of carbonation happening in your system. So, again carbonation of slag cements is generally higher than the carbonation of plain Portland cements. For example, here on the right, this is data that is published from a project that has been executed at our lab. So, you see here for ordinary Portland cement, the carbonation depth after 3 years of natural carbonation exposure. So, we simply took the specimens and exposed them to the natural environment on our terrace, BSB terrace, and you can see from that after 3 years the ordinary Portland cement mixes were, or the specimens prepared from the ordinary Portland cement mixes were showing an average carbonation depth of around 7 millimeters, whereas the mix with 30% slag was marginally higher, probably at around 8 millimeters, with fly ash again marginally higher, probably around 9 millimeters. Now, of course, this is not a significant difference at the end of 3 years, but if you put this in service life models, you will actually get a factor that is showing a lower service life for slag and fly ash based systems in carbonation environments. Please remember, most service life models are basically restricted to determining the service life as an equivalent of the time it takes for the steel to start corroding. So, here the time it takes for steel to start corroding here is assumed as the time that the carbonation front starts from the surface and reaches the level of the reinforcing steel. Okay. What does carbonation do? It consumes lime, right? You have calcium hydroxide plus carbon dioxide, that leads to formation of calcium carbonate, and of course, there is a water molecule that goes out in this reaction, but then again this is not indicative of the actual process that takes place. We will discuss that later. Some moisture is actually needed to convert this carbon dioxide into carbonic acid that actually consumes the lime. Okay. Now, this lime is already reduced in a pozzolanic system or in a cement substituted system. You have less lime available, right. So, if the carbon dioxide cannot react with lime, what will it do? It will tend to react with other calcium bearing compounds like CSH. Okay. And because lime reaction with carbon dioxide leads to the formation of calcium carbonate that almost forms an impermeable layer on the surface of the cement mortar or cement concrete. So, that becomes a limiting process. It further slows down the rate at which your CO2 actually goes in. In the case of mineral admixture based systems, since you have less lime, there is obviously going to be more CO2 going in. So, the carbonation depth generally in mineral admixtures will tend to go up as you increase the levels of replacement of cement with mineral admixtures. So, it is not really a secret, but that happens all the time. So, generally with most mineral admixtures, what you will see is that the resistance to chloride induced corrosion is always improved, but the resistance to carbonation or carbon dioxide penetration is generally reduced whenever mineral admixtures are used as a replacement for cement. Now, that is an important thing, because very many times if we take the rate of carbonation as an indicator of the possible damage you can expect in your system, then mineral admixture based concretes will always come out to be poor with respect to ordinary Portland cement based concrete. However, if you link carbonation to corrosion, that may still not be the case. Why do I say that? Because for corrosion process to sustain itself, you need the presence of oxygen and moisture. And where are these coming from? These are again coming from the cover concrete, and if the cover is dense and impermeable like what we expect concretes with mineral admixtures to have, your moisture will still be limited to propagate that corrosion. So, all this is saying is that the risk for corrosion can be greater in the case of concretes with mineral admixtures in a highly carbonating environment, because more carbon dioxide penetration can happen. But that does not necessarily mean that corrosion will actually happen, because the access to moisture could be quite limited. Okay. So, there is ongoing research which is trying to explore the humidity of concrete inside systems with different types of binders. So, humidity level obviously determines the rate of propagation of corrosion. If you have less humidity, very highly resistive concrete, then obviously you are not going to get great risk of propagation of corrosion. Okay. Now, of course, there is another research data presented here from Lai et al. At 2016. So, again it talks about increasing levels of cement replacement, and again increase in carbonation with respect to Portland cement in percentage is given here. You can see for fly ash there is a significant enhancement. For slag also the carbonation extent can go up, but it is not as much as that with fly ash. Okay. So, larger replacements of fly ash will produce greater risk of carbonation, whereas larger replacements of slag will produce marginally lesser risk of carbonation as opposed to fly ash. So, we have done an extensive durability study at IIT Madras with a number of different types of durability parameters. Some of these tests of course we will discuss when we actually get to the chapter on durability, but for now I just want to put some results in perspective so that you can get an idea about how these concretes perform when you replace cement with slag or fly ash. So, there were several different test methods that were conducted for a range of different concrete mixes. We had totally about 41 different concrete mixes that we used. So, here if you look at the surface resistivity, which is done by a simple technique called the 4 probe resistivity test. As you increase the extent of replacement of cement with either fly ash or slag, the resistivity enhances significantly. This is actually a result that is encompassing all different concrete mixture designs and all different types of mineral additives. Okay. So, here we see that there is a major enhancement in surface resistivity when cement is replaced by mineral admixtures. The impact of curing is all that more seen here, because from 28 to 90 days there is a steep increase in the resistivity of concretes with mineral admixtures. Okay. Whereas, if you look at not 28, from 30 to 50%, from 28 to 90 days is this increase here. The black line is 28 days and the red line is 90 days. So, from 28 to 90 days, as the level of replacement of cement increases, there is a greater enhancement of the durability. That shows that extended curing with mineral admixtures can be very helpful. Of course, nobody is going to cure for 90 days on the site, but all this goes to show is the longer you cure, the more the benefits you can actually get from the concretes with mineral admixtures. Similarly, if you look at chloride penetrability in terms of charge passed, there is a decline in the charge passed as you increase the levels of replacement. So, what is interesting here is that this very low charge passed of between 1000 and 2000 coulombs is being obtained by with a concrete. If you just have plain ordinary Portland cement, it is being obtained by the concrete with 400 kilograms of cement and 0.4 water binder ratio. So, what would be the grade of that concrete? 400 and 0.4, maybe about M40, M45. But here the next point here is 310 and 0.5 water binder ratio. If you are replacing cement with 50% of mineral admixture, you are getting an increasingly even better durability performance as compared to the plain Portland cement mix. But all this is happening at a lower binder content and a higher water binder ratio. What does this tell you? That even with a lower grade of concrete, what do you think will be the grade of this concrete? 310.5, maybe 30, yeah, maximum 30. So, M30 concrete with mineral admixtures at 50% replacement of the cement, you can actually get a durability performance that is equivalent to an M40 or M45 concrete with just plain Portland cement. So, this is exactly the study that I was reporting to you earlier. I mean, related to the study that I was reporting to you earlier with this construction company that employed fly ash as a replacement of aggregate because they were not allowed to be using it as a replacement for cement. All they wanted to do was get a lower charge passed in this test, which was not possible with just plain Portland cement for that grade of concrete. Okay. So, again mineral admixtures can help you make concrete which is lower grade also quite durable. That is the main impact of mineral admixtures. Again, there are positive results on water sorptivity. You also have positive results on other chloride bearing parameters. So, what we ended up doing is we looked at the entire set of data and did a qualitative ranking, which helps us understand, okay, if you are looking at a particular durability problem like chloride penetration, what is the relative ranking of these different types of mixes that we have tested. So, compared to plain ordinary Portland cement, which is at rank 4, that means the lowest rank, the best performer is slag at 50% replacement or fly ash at 50% replacement for chloride penetration characteristics. For carbonation, obviously OPC is the best. Slag at 15% replacement does not seem to be much different as compared to OPC, but at 30% and 50%, the rate of carbonation of slag based concretes is significantly higher than that of OPC. Fly ash even at 15% is actually showing you a greater rate of carbonation as opposed to plain Portland cement, and the performance is even worse at 30 and 50%. So, what can the concrete engineer do, a concrete designer can do is look at this data and decide on what would be the right blend of ingredients for the particular service environment that the concrete is being designed for. Okay. So, for a marine environment, obviously I will be looking at these two characteristics, chloride penetration and water sorptivity, and again based on that you come to the conclusion that 50% slag would be the best mix, probably followed by 50% fly ash. But if you have a consideration of strength at 28 days as one of the parameters, then obviously the fly ash mix may not really make it, you may have to rely on the slag mix. We will see that example more closely when we go to the durability section. Okay, now let us look at the smaller or less used mineral admixtures. Okay. So, rice husk ash is one such mineral admixture which is used to a lesser extent, primarily because there are not too many facilities that can produce the right kind of quality that is needed for enhanced pozzolanicity. So, rice husk ash is the high reactivity pozzolan obtained by controlled calcination of rice husk. Now, what do you mean by controlled calcination? Where we can actually control the temperature of burning and the time of burning. So, the temperature has to be controlled in such a way that the silica that you get from this rice husk becomes amorphous. If you burn it at very high temperatures, there is recrystallization that happens, and then silica gets transformed into other crystalline components where it is not really usable in your system. Okay. So, field burnt rice husk ash that you see commonly on our rice fields, right? People who separate the husk from the paddy take the husk and use it as a fuel source, they are able to burn it directly. But that burning in the field is not very good because it is not controlled. Okay. They simply burn it, they do not really pay any attention to the temperatures and so on, and the time for burning also can vary significantly between sites. So, when you do that, you do not really get the kind of temperature control that you require to produce a concrete that is, or to produce a material that is having good quality amorphous silica. Okay. So, control is required. So, well burnt rice husk ash is a good quality pozzolan. Now, again, because it is agro based, that means it is derived from an agricultural product, there are obviously possibilities of finding a lot of unburnt carbon in the system. What happens is you need to burn it at a temperature which is not high enough to get rid of all the carbon as carbon dioxide. So, when you burn something, the carbon goes off as carbon dioxide, right. So, at certain temperatures you need to burn it to get the best reactive silica, but at those temperatures the carbon may not completely burn off as carbon dioxide. So, you need to be careful about unburnt carbon content in your rice husk ash. Okay. Now, generally if you look at the individual fine siliceous particles of rice husk ash, the average size of the particles are quite similar to that of cement, there is not much difference. Compare this to silica fume where the average size was much smaller than cement, but with rice husk ash the average size is nearly similar, but the particles have a very high surface area, 60,000 square meters per kilogram. So, obviously not being determined by Blaine air permeability, but this is by BET technique or nitrogen adsorption technique, 60,000 square meters per kilogram. So, this must be because the particles have a certain texture, because the size is similar to cement, but texture has to be quite different. It is going to have a lot of cavities and vesicles, because of which the surface area is extremely high. Okay. The particles are cellular with cavities and vesicles, and generally the purity of the system is very high. You have more than 90% silica present in the system. So, I will show you some data and then I will show you a picture. So, again rice husk ash is predominantly amorphous silica which is similar to silica fume, and you can see that there are different types of agro derivatives which can be used. I will also show you some results with bagasse a little bit later, and you can see that the silica content in the ashes in bagasse is up to a level of about 70 to 80%, whereas the silica content in rice husk is generally more than 90%. Okay. So, where is the silica coming from in your agro products? From the soil, right, because there is nutrients which go in from the soil. A lot of silica is also derived from the soil that goes up and rises into the structure of the plants. Okay. There is some strengthening of the plants that also happens because of the silica uptake by the plants. So, this after you consume the good part, that is a carbohydrate, the remainder basically consists of the silica, the husk or the external covering basically consists of the silica. So, even in corn you can get significant quantity of silica, but then you have to determine whether that silica is usable or not. So, generally these are the, this is on the left side you are given a physical and chemical characteristics of rice husk ash which is burnt at 600 degrees Celsius. Okay. So, again here you see average size in terms of nanometers is 150 microns, 150 nanometers. Average size, this is given in terms of the surface area converted to a size. So, it is not really the actual size of the particles. particle sizes are much larger than that, which is quite similar to cement. Specific surface area in meter square per gram is 77 meter square per gram. That means 77,000 meter square per kilogram. Okay, so imagine this is a very fine material that is being used, or a very highly reactive surface can be provided as long as you have the right kind of amorphous silica in the structure. Okay. Loss and ignition here is 3.13%. Obviously, this corresponds to the unburned carbon that is there in the system, right. And then silica content is more than 90%, and you may have some other impurities. Many of these agro impurities you can find significant amounts of alkalis, sodium and potassium oxide. Okay. So, again the alkali loading of the concrete needs to be checked carefully whenever you are replacing cement with agro waste. I will show you later about bagasse ash that the alkali content can be as high as 5 to 8% because of bagasse ash. Now, when you use that as a cementitious replacement, the overall alkali content has to be considered carefully. So, these are the Reiser's cache particles. You can see from the left that these particles are looking quite coarse. There seems to be some needle like particles also. Those are basically the unburnt carbon, okay, whereas the smaller dark colored particles are the silica particles. So, if you look at these dark colored particles or silica particles, they show you a very irregular texture, a lot of cavities and vesicles inside. That is responsible for the extremely high surface area of the Reiser's cache. Now, the other common mineral additive that is increasingly being used these days is metakaolin or burnt clay, calcined clay basically. So calcination or controlled burning of kaolinite between 750 and 850 or 740 and 840 degrees Celsius can lead to the transformation of kaolinite into metakaolin. So, again please remember, when cement is produced also, the clay that is introduced into the kiln undergoes an activation which allows it to combine with the lime and make the different cementitious compounds. In the case of metakaolin, this activation of clay is what is making it reactive, okay. And since clay is aluminosilicate, you again get mainly a pozzolanic reaction from this system. Of course, please remember here what you are doing is you are collecting the clay and then burning it. So, there is a major processing cost involved. So, processing involves burning of this clay, and that sometimes takes up a lot of energy, and because of that energy the cost of that material can be significantly large. So, usually what happens is metakaolin is available in the market probably about 30% lesser than the silica fume cost. Okay. So, we still pay about 20 to 25 rupees per kilogram of metakaolin. So, it could be quite expensive, but that is basically pertaining to the high purity kaolin. Where in what other industries would they be using calcined clay, calcined kaolin? Sorry, brick industry, of course it uses the topsoil, but here we are talking about kaolin. Brick industry uses topsoil, mostly it is illitic clay, it is not really kaolinated clay. Kaolinite is found in layers much below the earth's surface. So, you need to actually mine it to get it. Okay, so, this kaolinite can be mined and obtained and then burnt to form fired kaolin or calcined kaolin. Now, typical firing temperatures when you want to produce this calcined kaolinite is more than 1000 degrees Celsius. That leads to the formation of a very white crystalline powder, and this white crystalline powder can be used as a very good additive for stabilization of paints and for the ceramic industry. On China clay basically, right, what you call China clay is basically fired kaolin. This is fired at temperatures much above 1000 degrees, okay. But then that clay is not reactive as far as pozzolanic reactivity is concerned. For the clay to be reactive, you need to calcine it in this temperature range of 740 to 840 degrees Celsius. When you do that, the aluminosilicate gets activated, becomes amorphous, and is capable of reacting with the lime that is generated from cement hydration. Okay. So, fired kaolin, which is produced at graded temperatures, is used as an additive in paint industry and ceramic industry. Now, for that process they need a kaolin that is extremely white in color, okay. Very high purity kaolinite is what they need. They need kaolinite contents of more than 90%, and generally metakaolin also has kaolinite contents of, or is also produced from a clay which has kaolinite contents in excess of 90%. So, in these clay mines you do not always get this kaolinite or pure kaolinite separately, right. Many times it will be mixed with other impurities like quartz or iron oxide and things like that. A lot of the impure clay which cannot be processed for these industries is simply dumped as a waste. And later when we talk about limestone calcined clay cement, the main advantage there would be that we can utilize clay which is of a lower grade, which does not need to be very high purity kaolinite, which can be nearly 40 to 60%, and that can be used for the preparation of LC3, that we will get to in just a minute. Okay. So, chemical formula of metakaolin can be written as AS2, 1 molecule of alumina to every 2 molecules of silica. Okay. That is mostly all clays especially kaolinitic clays are of that formulation. Okay. And this compound reacts with calcium hydroxide to give you calcium silicate hydrate and calcium aluminosilicate hydrate. So, that is what you would have in your system. Okay. So, a lot of people have published data with metakaolin. Mostly the data seems to indicate that at levels of about 15 to 20%, metakaolin seems to perform quite similar to silica fume, which is used as a cement replacement. Now, here again clay being very fine ends up producing metakaolin, which is usually much finer than that of cement. Okay. So, typical Blaine air permeability for metakaolin would be of the order of 900 square meters per kilogram, 900 to 1100 square meters per kilogram. So, much more reactive as opposed to slag or fly ash, which are much smaller, again because of the very high purity aluminosilicate that you get from metakaolin. So, this is the reaction which has been studied by many people. So, here aluminosilicate, calcium hydroxide, water leads to the formation of calcium aluminate hydrate, and CSH, very often this calcium aluminate hydrate is mingled in the structure of CSH itself. So, you often get CaSH formation with the reaction of metakaolinite. Okay. You may also get other phases like I showed you earlier, you may get phases like stratlingite. Okay. In the beginning there was a ternary phase diagram that we talked about. Stratlingite is another calcium aluminosilicate hydrate phase. Okay. So, we have seen this before, that mostly what will happen is the pozzolanic CSH that is produced because of the reaction of lime with your pozzolanic material will have a calcium to silica ratio which is much smaller than that of Portland cement. Okay. Usual PC based CSH has about 1.7 to 1.8, whereas your pozzolanic replacement will produce CSH of the rate of 0.8 to 1, that is what you will actually get. Some results have been presented here of metakaolin. So, here this was based on some projects that we had done for a company that produces different grades of metakaolin, and we were trying to help them evaluate the best product for commercial use in the market. So, here we made concrete M60 grade and 80 grade concrete at different levels of replacement of cement with silica fume and different brands of metakaolin. And again you can see that mostly the performance of metakaolin and silica fume is more or less similar, marginally better than the reference concrete which does not have any silica fume or metakaolin, but more or less quite similar. Again with the M60 concrete also you get very similar results. There are some results which are probably quite high as opposed to the others, but for the most part we are getting similar results with most of the concrete mixes. But the impact once again when you use a mineral admixture is seen better with respect to durability than with respect to strength. For example, here the charge passed in terms of coulombs, if you look at replacement with silica fume at 5, 10, 15 and 20%, you can see a massive reduction as opposed to the plain Portland cement which is over 2000 coulombs. Okay. Again with metakaolin you get numbers that are quite low, quite similar to what you have with silica fume. So, there is not much difference with respect to performance as far as comparison with silica fume is concerned. Okay. These days in if you go to the Mumbai area, there is a lot of use of high performance concrete and high strength concrete, mainly for their skyscrapers. There are very tall buildings that come up in Mumbai all the time, and for that, for the lower ground stories, it is always useful to actually go for a high strength concrete. They go for strengths as high as M90, M100 and things like that. Okay. So, when they go for such high strengths, obviously they need very finely divided mineral additives in the system like silica fume. Metakaolin is another option, and today they also have one more option called ultra fine slag. Ultra fine slag. Now, ultra fine slag can also help them enhance their strength potential quite well. For example, concretes of grades M90 and M100 can be produced with ultra fine slag. Interestingly, it has been seen that the reduction in workability that you typically see with silica fume and metakaolin will not be the same with ultrafine slag. You do not see the same reduction in workability, you see a slightly better performance when ultrafine slag is used. However, at the same levels of replacement, let us say 5 to 20% replacement, ultrafine slag can never get you these kinds of numbers, can never get you the kind of numbers that are showing extremely low rapid chloride permeability. Okay. But in terms of other durability characteristics, for example, the sorptivity or water absorption potential, you may get similar performance characteristics. But with RCPT, ultrafine slag does not give you the same result as silica fume or metakaolin. Again, this is mainly because silica fume and metakaolin, the finely divided grains, can actually capture the alkalis quite effectively and lower the conductivity of your system tremendously. Slag can do that to some extent, but not as much as silica fume or metakaolin. So, again as a high performance mineral additive at different replacement levels, the strength increases significantly when silica fume and metakaolin are used as cement replacement. Generally with metakaolin, again you get extremely good resistance to chlorides. No surprise here, because metakaolin provides reactive alumina that is again able to bind the chlorides in the concrete and prevents the chlorides from reaching the surface of the reinforcing steel. So, with carbonation, what do you expect? Carbonation resistance will generally tend to reduce when metakaolin is used, because again you are consuming lime rapidly, okay. You are consuming lime rapidly. However, the increase in your impermeability of the concrete may offset that to some extent, offset the carbonation resistance to some extent. Okay, so today increasingly many countries are adopting limestone itself as an additive to concrete, to cement in concrete. Now, why do they do that? It makes economic sense to do that, because first of all, this limestone is already available at the cement production unit, right. You do not need to burn this limestone. Burning requires energy, burning pollutes by putting out carbon dioxide, right. So, instead of burning and spending more energy, you take the material that is already available at the plant and use it as a partial replacement for cement. Now, already you know very well that even in ordinary Portland cement, up to 5% of performance improver is permitted. That is the most often used level of limestone, at least in India. But if you go to the western countries, they permit a much higher level of limestone replacement, and they call the cements as Portland limestone cement. In India also, a draft standard is being prepared, and this may become a reality in the near future. Portland limestone cement. Here up to 15% replacement of cement with limestone is happening in most countries. However, if you look at EN standards, it permits 6 to 20% replacement of cement with limestone. So, up to 5% anyway is permitted in ordinary Portland cement itself. When you call it a Portland limestone cement or a composite cement as per EN standards, you are permitted up to 6 to 20% replacement. So, 6 to 20% means you can have a significant reduction in the amount of CO2 that is getting emitted from your cements, and lower the overall CO2 potential from the concrete as a result. Mainly if you consider cement to be the main contributor of CO2 emissions, you can reduce overall signature of carbon dioxide emission, right. Problem is, if you go higher and higher with limestone additions, you are simply replacing cement with a mostly unreactive material. So, what will happen is the filler effect can only help to a certain extent, but beyond that, since you do not have a reactive material, you may not really get the kind of performance that you want with plain Portland cement mixes. So, with very high replacement levels of limestone, there is a significant reduction in performance. However, that does not mean that we can't use it. Even for low grade concretes, like for residential construction, we may actually end up finding satisfactory performance from limestone based concrete mixes, with limestone contents even as high as 30 to 40%. If you take that in terms of the life cycle cost, your overall system may be much more effective than a plain Portland cement based system. Okay. Obviously, there will be a strength reduction because limestone is not going to be reactive. The reactive component of the strength will not be getting obtained because cement is being replaced by limestone. When we see the next chapter on high performance concrete mixture design, you will see that the filler effect is able to some extent overcome the lack of reactivity that you see from most of these filler materials. If the material is both reactive and finely graded, then it provides you much better benefits, obviously like silica fume or fly ash or slag. But with just fillers, you may get an enhancement only up to a certain level. Now, this of course is not very useful, so we will not look at this further. What we will talk about is the use of limestone in ternary systems. So, ternary implies how many components? 3 components. So, that means of course one component has to be cement plus limestone plus what? Mineral additives like fly ash or slag or metakaolin or silica fume, right. So, there the third component is your supplementary cementing material. Now, this system of combination of cement with limestone and supplementary material has been looked at very closely over the last 5 to 10 years, and there has been growing interest in looking at these ternary blended systems as a possible solution to lowering the amount of cement that needs to be used in concrete. Now primarily this has come about from the perspective of reducing the CO2 emissions and lowering the carbon dioxide footprint of concrete. Okay. So here this combination of ternary blended limestone and supplementary material can actually give a very unique sort of a performance. So again, limestone addition brings in a slightly new chemistry. There are additional hydrate phases that can actually form in the system and better filling characteristics. Now what am I saying here? Earlier I was telling you limestone is simply sitting there as a filler. I am now saying that it is reactive. So what does it react with is something that we need to look at. So again, since limestone is available at the cement plant itself, there will be cost effectiveness associated with this process. So now what phases form when regular cement hydrates? So mostly clinker phases which have a density of 3 to 3.2, right, 3.15 is the average density, produce different phases like CSH, you have calcium hydroxide, ettringite and AFM. So I want you to pay attention to the densities of these materials. If you look at ettringite, it has got the least density 1.77. What does that mean? If you form ettringite, it will fill up more pore spaces. It has got low density, so it fills up more spaces. Okay? Whereas CSH is the highest density phase. Of course, we can't live without CSH because it is the primary binding phase of your cement paste. Now what happens when I substitute these with a ternary blended system? When you have limestone and a supplementary material, what is going to happen next? So I still form my calcium carbonate out. You have calcium silicate hydrate which is still forming because of cement hydration. You have calcium hydroxide, you have ettringite, you have AFM phases which are still there because of cement hydration. But additionally you also form calcium aluminosilicate hydrate because of this supplementary cementing material. You form two phases which are called monocarbonate and hemicarbonate. And these are forming because of the reaction of limestone plus aluminate. Limestone implying the CO2 from the limestone plus the aluminate is forming the monocarbonate and hemicarbonate. So again, if you look at it, these are also AFM phases. They are quite similar to AFM type phases. Please remember what happens when AFM is formed. Aluminate reacts with sulphate to form AFM. Here aluminate reacts with carbonate to form AFM phases where you have carbonate and not sulphate, same sort of phases. Okay. So now the interesting part is whatever aluminates were there in the system in the early phase start getting used up to make monocarbonate and hemicarbonate. If you do not have an excess aluminate in the system, what will happen to ettringite to monosulphate conversion? That will reduce, right. Why does ettringite convert to monosulphate? Because there is excess aluminate present on top of the sulphate. Now what we have done is shown the aluminates a different path. They go and react with the carbonates to form monocarbon aluminate and hemicarbon aluminate. So what we are doing is stabilizing this ettringite component in the system. So that means we have more pores that are filled because of ettringite being stable, and then we have additional hydration products that are still going to fill up more pore spaces. Monocarbonate and hemicarbonate are filling up additional pore space, okay, and this effective filling of the pore spaces obviously is going to enhance your strength and durability characteristics. Okay. So you can expect that your strength and durability with a ternary blended system involving limestone and a supplementary cementing material that provides reactive silica and alumina can be expected to be really good. Okay. So what are the aluminosilicate based inorganic additives that you can work with? Again, fly ash, slag, calcined clay. So basically this is either fly ash or slag or calcined clay. So where do you think the alumina is most reactive amongst these three? Fly ash, slag or calcined clay? Which system gives you the most reactive alumina? It is a calcined clay which gives you the most reactive and significant proportion of alumina. So again, the main benefit that you get from the system is when you use limestone in combination with calcined clay. So here what you are doing, again just to put this in perspective with this picture that we saw earlier, that when regular cement hydrates you mainly form CSH, you form calcium hydroxide, you form calcium aluminate hydrates, you form monosulphate, and usually ettringite goes down as monosulphate is formed more and more. So when you add this ternary blend, when you have this ternary blend, you still have the same reactions, but the ettringite no longer starts depleting, it continues to remain at the constant level. Your monosulphate formation does not really happen because your aluminates have gone into reaction with carbonate to form monocarbonate. So, you have monocarbonate formation which takes up the space which was meant for the monosulfate. So, you have ettringite. So, what are the stable products you have? You have also one more thing is obviously your lime content goes down because your pozzolanic reaction is going to happen and your CSH content will go up. Okay. So, essentially in the end you will be ending up with CSH, calcium hydroxide much lowered as compared to plain Portland cement, right. You will have ettringite, you will have monocarbonate plus hemicarbonate, or you may have one of the systems. Again, hemicarbonate is 0.5 carbon and this is 1 carbon, right. Monocarbonate means 1 carbon, hemicarbonate is 0.5 carbon. So, usually one or both of them are stable in the system. Mostly monocarbonate will be ending up being stable in the system. Apart from this, you will again have the calcium aluminate hydrates, so calcium aluminoferrite hydrates if that is permitted, right. So, that will be the end component of your system that has the ternary blend of cement with limestone and supplementary cementing material. So, again stabilization of ettringite happens, there is an increase of carboaluminate phases, lowering of the Portlandite content and increased CSH and calcium aluminosilicate hydrate, that is generally going to be driving the porosity even further down. You are going to expect that the system will actually produce much lower porosity as opposed to ordinary Portland cement system, and when you have lower porosity obviously it translates into better durability and strength. So, again this is just capturing the effect of limestone usage. You have the filler effect obviously where the limestone particles provide efficient particle packing and reduce the capillary void space. As if you consider the chemical effect, the calcium obviously increased amount of calcium leads to the nucleation of calcium silicate hydrate on the small particles of the limestone itself, whereas the carbonate leads to the formation of monocarbonate and hemicarbonate. Okay. So, again you have overall a very positive role for limestone to play in the cementitious systems, and more than that limestone causes reduction in CO2 emission, because you are no longer burning the product, you are no longer processing the product. Because of that, when you replace cement with limestone, you are essentially getting a much better CO2 emission performance. Now, what about regular Portland cements? I said up to 5% limestone could be there. Would there be any possibility of reactivity to form monocarbonate or hemicarbonate in those cases? Where is the aluminate coming from there? The C3A? The C3A in cement can give aluminate which is reactive again. C3A can react to some extent with limestone and lead to the formation of monocarbonate and hemicarbonate phases also. There is a possibility that can happen. Okay. So, because of that you also get some benefits of that performance, but the 5% level is not high enough to give sufficient amount of calcite, to give sufficient amount of calcium carbonate for reaction. That is why we want to go for limestone contents in the range of 10 to 15% to optimize the extent of calcium carbonate that is given for reaction in the system. So, again the expected impact of limestone when used in combination with other SEMs, first of all it can improve the flow properties or rheology when difficult supplementary cementing materials such as calcined clay are used. So, calcined clay extremely small particles, and you know that clay has a layered particle system. So, that those layers basically capture the water and superplasticizer and prevent good workability of these systems. So, when limestone is used, that brings the workability to a much more acceptable level. Low early strength and fly ash systems can be compensated to some extent by increasing the reactivity with limestone, utilizing the blend with limestone to reduce the extent of damage caused by increased levels of replacement of fly ash. And you can definitely expect improved performance in sulphate attack because monosulphate phase is not forming. So, you do not have possibilities of ettringite forming in the long term. Okay. And obviously chloride exposure, because you have a lot of aluminate in the system, this aluminate is going to be reacting with the chloride to form chloroaluminate phases, binding the chloride, preventing it from reaching the surface of your reinforcing steel. And definitely there is going to be a possibly lowered resistance to carbonation because your calcium hydroxide is getting consumed tremendously. So, your CSH phases will start getting attacked by the carbon dioxide. So, again this led to the basic understanding of the science of the ternary blends led to the development of what we call as LC3 or limestone calcined clay cement. Now, this development obviously looks at the utilization of the pozzolanic properties of metakaolin, and in addition the reaction of the metakaolin with limestone, that is calcium carbonate. So, here you have the alumina and the calcium carbonate in the presence of lime. Okay, please remember here even this alumina and calcium carbonate reaction requires the presence of lime for the formation of this system, which is, what is it, hemi or monocarbonate? One carbon is there, so it is a monocarbonate, yeah, that is a monocarbonate. So, this is presenting some preliminary research results from this project, which was done about 5 to 10 years ago. This was originally started off as a collaborative project between Switzerland and Cuba, and they were trying to look at different types of clays. They also got some samples from India and Thailand in this case. So, here they have very pure kaolinite content, that means 95%. So, obviously, the kind of grade of kaolin you will get is metakaolin grade. Okay. From India, the kind of clay that they had was 80% kaolinite content, and there was one with 20% kaolinite content, and from Thailand they had 50% kaolinite content. So, look at what happened at the one day. So, this is plain Portland cement without any additive at all. So, here B45 implies there is 30% of calcined clay and 15% of limestone. 45 means 30% calcined clay and 15% of limestone in the system. So, when you do it with the high purity metakaolin, by 3 days you are able to get a strength which is better than Portland cement system, and by 7 days it is significantly better than the Portland cement system. What happens with the 80% clay or 80% kaolinite? Slightly lesser than cement at 3 days, but by 7 days there is a major enhancement in the strength. Even with the poor quality clay with 50% kaolinite content, you are still getting performance which is little bit lower at 3 days, but at 7 days it is marginally higher than that of the Portland cement system. So, if you want to match the performance of Portland cement system with 45% total replacement, this is possibly giving you the best solution. Okay. With 50% slag, you may get some of these characteristics, but with other alternatives like calcined clay, because if you remember we discussed earlier the availability of different types of materials, the availability of slag is much less as opposed to the availability of clay, potentially calcined clay. Okay. So, we have to look at clay and then convert that to calcined clay. Now, interestingly, even with the 20% kaolinite system, there was only a difference of about 20% or 25% as opposed to plain Portland cement. Now, what does this tell you? You are replacing cement by about 45% of this blended material, limestone and calcined clay, but you are actually getting a performance that is only 20% less. Okay. So, even with low grade kaolin, you can still produce a cementitious combination that is capable of giving you a significantly good strength. So, you can still work with the cement, for instance. Okay. So, here in EPFL in Switzerland, where the primary research on this material was done, they also tried to understand the effect of the calcined kaolin content on the performance of mortars, okay, in terms of the compressive strength. So, they have these figures for 1 to 90 days of strength. So, if you look at the 1 day strengths, there is definitely a benefit of increasing the levels of calcined kaolinite content. Obviously, more the kaolin, the better the reaction, and you get a much better performance with respect to higher levels of kaolin. But what we wanted to see was where we should really cut off, because we can't obviously go for the high grade clay, then that will totally turn this in the same direction as that of metakaolin. So, it is not going to be cost effective anymore, and the use of high purity clay which could be used in other industries does not make sense. We want to make use of the material that is not capable of being used for the ceramic and paint grade industries and utilize the impure clays for their performance in this ternary blended system. What we found was clay with 40 to 60% kaolinite was sufficiently good. For example, at 1 day you do not really see a major difference, and at 90 days your performance is only marginally lower than if you had 90% kaolinite in your system. So, at 40 to 60% you can actually maximize the potential of this material without really having to bother with producing higher grades of clay. We will continue from here in tomorrow's class. Thank you.